Good morning, everyone, and welcome to EDP and Applied Mathematics Seminar. It's a pleasure for me to open session 76 of this seminar. Today we have two excellent speakers, the Professor Yihong Du and Professor Miguel Núñez. Introducing Yihong Du, we have to Professor Diego Souza. Thank you, Diego. You can start.
Okay, thank you very much, Juan, for the opportunity to introduce Professor Yihong Du. Let me just say some words about Professor Yihong Du. Professor Yihong Du is full professor at the University of New England in Australia since 2008. Professor Yihong Du is an expert in mathematical analysis. He has interest in many mathematical problems with applications in biology, invasion ecology, chemical reaction theory, among others. He worked precisely in nonlinear elliptic and parabolic PDEs with some free bounded problems. And today, Professor Yihong Du is going to talk about a long-time dynamics of two invading competitors. So thank you very much, Professor, for accepting talking in our seminar, and you can start.
Hey, thank you. Thank you for the introduction. And also I'd like to thank Professor Juan Limaco for inviting me to give a talk in this seminar series. It's a really great honor for me. Today I'll talk about the dynamics of invading competitors. So when two competing species invade into unlimited space, so the traditional model is this so-called Lotka-Volterra competition system. So here we have a U and V, which represent the population densities of two species, and so we assume they have a competition relationship. And so each of these unknown functions, so U and V similarly represent the population densities of one of the competitors at time t and the spatial location x. Here we have 8 parameters, D1, D2, A1, A2, B1, B2, and C1, C2 in symmetric positions. They are all positive constants, and the meanings are listed here. So D1, D2 are the diffusion rates. So D1, the diffusion rate of U, D2, the diffusion rate of V. And A1 is the growth rate of U, A2, the growth rate of V. And B1, B2 measure the strength of intraspecific competition with the members of itself. And C1, C2 represent the interspecific competition. And C1 measures the competition U feels from V. And C2, the competition from U to V. But for mathematical analysis, we can reduce the number of parameters from 8 to 4. So we do these scalings, and then 1 can be reduced to the equivalent 2. But here we have only 4 parameters, D, alpha, B, and A. Again, all of these 4 are positive, obtained in this way. So from now on, we will just look at this system of reaction diffusion equation, the simplified one, which is equivalent to the original model here. And looking at this model 2, and we can say immediately there are some constant equilibria and u equals 0, v equals 0, that's 1. And also 1, 0, 0, 1, these are also constant equilibria. And if these holes, that is, either A, B are both less than 1 or greater than 1, then this U star V star is a meaningful equilibrium. Meaningful because both components are positive. Because we are densities, so only non-negative equilibria makes sense. Now, to understand the dynamics of this PDE model, then this PDE model, and it helps if we look at the corresponding ODE problem. So the ODE problem, we just forget about the diffusion terms, we have this one. The long-term dynamics of this ODE problem actually is clear. So of course, we assume the initial state are just a positive constant, U0 positive, V0, because now we are considering the ODE problem. These U and V are functions of time t. And with the positive initial data, the long-term dynamics of this ODE problem is clear, depending on the values of A and B here. So we have a B, we have A. If B is less than 1, A is greater than 1, then when t goes to infinity, U convert to 1, V convert to 0. In case 2, it's the other way around. U convert to 0, V convert to 1. If A and B are both between 0 and 1, and then U and V convert to these positive coexistence state. If A, B are both greater than 1, then the location of the initial values matters. Depending on the location, and this limit could be 1, 0, or 0, 1, or the positive steady state, U star, V star. Actually, we know there's a curve, continuous curve in the first quadrant of the plane of the AB plane, so that if the initial function, these two values form a point on the plane, if this is below this curve, it converts to 1, 0. Above the curve, convert to 0, 1. If it sits on the curve, the initial value sits on that curve on the UV space, two-dimensional plane, then it converts U star, V star. And because of this dynamical behavior, and case 1 and 2 are called a weak strong competition case, determined solely by the values of A and B, the interspecific competition parameters. And case 3 is called a weaker competition case. In that case, the two species coexist at this equilibrium in the long run. And case 4 is called a strong competition case. And depending on where they start initially, it ends up in different state, 1, 0, 0, 1, or U star, V star. Now coming back to these, so I just mentioned the simplified ODE problem. For that problem, we know the long-term dynamics completely. Now coming back to 2, this is a reaction diffusion model, and space matters here, so its long-term dynamics is not that simple. Now, recall that we are interested in the invasion behavior of the two spaces. We assume U and V are invading the infinite space Rn. In that setting, and the space variable runs over Rn, and we also require initially the population concentrate locally. And then we look at how the population range of U and V evolve in time. So what's the population range of U and V? Well, for any given time, the population range of U is those places, those locations X where the density is positive. Similarly, the population range of V consists of those X where the density is positive. And at the time t equals 0, well, that's the initial population range. We assume these are bounded set in Rn, meaning that the distribution of the population are localized. And then we consider how they invade the unlimited space when time t goes to infinity. But there's a problem. Because of the strong maximum principle, and with these kind of reaction terms, we know that once t is positive, this set is the entire Rn. So therefore, the population range becomes Rn immediately from 0 once t is positive. Even when t equals 0, as time equals 0, the population is localized. Of course, that's not realistic, but we can circumvent this problem by nominating a very small positive constant delta and regard this set as the population range. So not greater than 0, but greater than some positive, small positive delta. No matter how small is this delta, and this set is no longer Rn. It is bounded for any finite t. So that looks more like the real situation. The population range are bounded. And one fortunate thing is that if we use these to represent the population range, and then we can find a spread invading speed. How these invade the unlimited space. They have a speed. How to find the speed? The speed is determined by looking for traveling waves. And for the weak strong competition case, like in case 1, we mentioned a bit earlier. In that case, and it is known that the system, the competition system, has a traveling wave solution with a minimal speed c. C is uniquely determined by traveling wave solutions. And this minimal speed is the speed these set, the population range, invade the available space. Actually, in this case, 1 invade, so U, because this is a weak strong competition case, actually, V invade and V retreat. So the competition case. And this speed c does not depend on this delta. So that shows the value of this model too. So it gives us an invading speed which does not depend on this nominated delta. But of course, if you care very much about the population range, then it's not only the speed, this set also matters. And then, of course, this model too is not adequate. To overcome this problem, one natural way is to introduce a free boundary problem, where the population range is exactly the region where the PDE are satisfied. And the boundary of the population range evolves with the time, as in a real situation, the population range invade the unlimited space. But then, of course, the price you pay is that you consider, instead of a Cauchy problem here, instead of this Cauchy problem, you consider a free boundary problem, which is much more difficult to treat in mathematics. Nevertheless, in many situations, if we consider one space dimension or in high space dimension, but we consider the radially symmetric situation, then the regularity of the free boundary, that's the main technical issue for a free boundary. This disappears. So we can still concentrate on the dynamics. So that's what we'll do. So we will consider the same reaction diffusion system, but over changing domains. So the changing domains here are balls. We look at the radially symmetric situation. So the population range of U is a ball of radius S1t, changing with time. Population range of V is a ball with a radius S2t. And we assume outside of this population range, the population density is identically 0. And because this is now a free boundary problem, we have to introduce equations to govern the movement of the boundary. And here we use these one-phase Stephan problem. So now here, the Laplace R really means this radially symmetric Laplacian operator is given by this. So we concentrate on radially symmetric solutions, and therefore the free boundary is a sphere of radius here S1t, here S2t. So they are smooth. So we don't have to worry about their regularity. And then we can concentrate on the long-term dynamic behavior of this system. So this one-phase Stephan condition was originally used for the case that ice melting in contact with the water. And in the current biological context, by making reasonable assumptions in this paper, so these conditions are derived from suitable biological assumptions. And I say biological assumptions is because with a biological problem, there's a lack of first principles. There are no first principles telling us how populations behave near the range boundary. So we have to make suitable assumptions, and with reasonable biological assumptions, we can derive these conditions. And this mu1, mu2 has some biological meanings. Basically, it measures how much the population sacrifice in order to invade, to expand their range boundary, their population range. So mu1 is well, 1 over mu1 is proportional to this sacrifice. The more the sacrifice, the smaller the mu1. That's for the U species. For the V species, it's similar. The more the sacrifice, the smaller the mu2. Also, because we have so many cases, so in this talk, I will concentrate on the weak-strong competition case. So we assume A is greater than 1, B is less than 1 in this model. So that's the model. Here we have A, B, and so A greater than 1, B less than 1 means U is strong, V is weak. In the ODE case, U wipes the V out and establishes itself in the long run. But of course, in the PDE case, the dynamics is more complicated, and we will see what will happen. In the case n equals 1 in one space dimension, Guo and Wu, they showed that under condition H with strong competition, A greater than 1, B less than 1, the dynamics of the problem, now the free boundary problem, so this problem in dimension 1, can have only 4 possibilities. Either both species vanish eventually, so the population range stays bounded, so it's a limit, so range bound, range radius, so the radius converts to something bounded, and the density converts to 0, so vanishing, both species vanish. Or U vanishes and V spreads successfully. In that case, I'll describe it more precisely. Actually, V goes to 1, U goes to 0. And also S1T, the population range radius of U converts to a finite number. The population range radius of V, S2T, converts to infinity. And 3 is the other way around. U vanishes and U spreads successfully. And the last situation is the most interesting one. Both species spread successfully. As I mentioned, for 2 and 3, that can be described very clearly mathematically, but not for 4 in here from this paper. So in 4, you can only show the range radius converts to infinity, and the population does not vanish, but you don't quite know exactly how the population distribute. And also, though these, these convert to infinity, you don't quite know at what speed they go to infinity. So now the purpose for today is to describe some recent result, showing how we can better understand this case 4, the most interesting case. Now, to understand this case, we actually have to go back to look at what is known. There are 2 kinds of existing results which are very, very important. The first kinds are the single species model. So if in problem 2, in problem, I think is a free boundary problem 3, if V is identically 0, so this problem reduced to a single species free boundary problem. We have only U here, so this is 0, and V is identically 0. So we have, this is reduced to a problem of this type, 1 species with a free boundary. And this situation actually was considered by myself and Professor Zhigui Lin from Yangzhou University for case n equals 1, and also with Zhongmin Guo for high dimension reduced symmetric situation. If we drop the reduced symmetry assumption, this problem becomes rather technical. And that was considered by myself and Zhongmin Guo, and also in joint work with Hiroshi Matano from Japan and Clay Wang from China. And there are many people consider various generalizations of this problem. But today, because of time limitation, I'll just mention the main result for 5. So we know there exists a unique solution defined for all time. And for long-time dynamics, we have a spreading vanishing dichotomy. Either the radius of the free boundary converts to a finite number and the population density converts to 0, or the radius converts to infinity and the population density converts to 1. So the second case is the spreading case, and the first case is the vanishing case. You say the density converts to 0. Moreover, when spreading is successful and this ht goes to infinity, like linearly in time. So this mu, k mu is a uniquely determined constant. And the density function can also be determined by some function q. And these k mu and q actually form a pair of traveling wave solutions. So Q satisfies these ODE and with these boundary conditions. And it is proved that so this problem has a unique solution pair. K mu determines the speed of the spreading, and Q determines the density profile. This is called a semi-wave. And actually, this result has been significantly improved in this later work with Matsuzawa and Zhou. And we can show HT minus K mu T minus this log T correction term, some constant K mu tilde times n minus 1 log T plus some constant. These convert to 0. This is a better description of how HT goes to infinity than 6. Now, how can we use these 5 to our problem 3? Well, using 5, we know in the case when U vanishes, V spread successfully, that's case 2, and we know much more. So we know now S1 converts to a finite number, and U converts to 0. So that's for species U. That's about its range radius, that's about its density. For V, it converts to 1, and the range radius goes to infinity. And moreover, this range radius goes to infinity with some linear speed, S mu 2 star. S mu 2 star is determined by these by 5. You look at there's a spreading speed with a U absent. So that's for V. And that's determined like what I mentioned here, these K mu like. Yeah, you consider the one dimension K, one species case. For U, you get, for V, you get S mu 2 star. And for U, you get S mu 1 star. So these are from the one species model. And another very useful auxiliary problem is this case, where V is a native competitive U. We again consider 2 competing species, but we assume U invade the unlimited space where there's a competitor already there. That's why V's population range is the entire space, and U's population range is this ball with the radius S1T. That problem was considered actually earlier, and we have this conclusion. So if the native competitor initially has a population density bounded below by 0, and then in this paper we proved that then when U invaded successfully, then the spreading speed of U S1T over T is determined by some constant C mu 1. This C mu 1 is determined in a very complicated way. You look for traveling wave solutions. Because of a time limitation, I think I'll just skip these details. But we just remember that from these auxiliary problem 7, we have a C mu 1, a constant. So that will be very important for us to understand the problem at hand, that is 3, the 2 species competition model with the free boundaries in the radially symmetric setting. We have a C mu 1 from 7. We have a S mu 1 star from 5 for single species situation. So here, S mu 1 star is obtained when V is identical to 0, and we consider the single species situation U. There's a spreading speed. And S mu 2 star is the spreading of V from 5, where when U is absent from 3. So now we know these 3 parameters, 3 numbers from auxiliary problem, not direct for 3, but they turns out to be very, very important for the understanding of the dynamics of a thread. And in 2018, in joint work with Changhong Wu from Taiwan, we proved, using these parameters, we proved that, so if C mu1 is greater than S mu2 star, then at least one of the two species, U and V, must vanish. So therefore, this case is not interesting to us because these cases are already clear. If S mu1 is less than S, C mu1 is less than S mu2 star, then we found interesting situations happen. We found some initial functions for which we can understand the coexistence state of the two species. And we can show actually there's what we call a chase and run coexistence state. So U spreads at speed C mu1, and V speeds at this higher speed S mu2 star. And that's why we call it chase and run. V is the weak competitor, but it runs faster, spreads faster. U is the strong competitor, but it's spread slower. So it gives space for V to run, to survive. Basically, it's like that. So I'll explain more precisely this behavior in a moment. But this really is a kind of a first breakthrough. So we know how actually these two species coexist and how fast they run and how the densities distribute. However, the initial conditions we found in this paper are very special. A natural question is that if we choose the initial functions differently, can we have other coexistence state? And we, at that time, we really didn't know because we only for very special initial functions, we can understand the coexist state. And in joint work with Dr. Khan, Dr. Liu, and Dr. Schaaf, we looked at this problem numerically. We tried to search to find a new coexistence state, but we didn't find anything new. So therefore, the numerical simulation seemed to suggest that, so though you found these chase and run coexistence with the very special initial functions, but even with the very general ones, perhaps you don't have anything new. The only coexistence state is this chase and run coexistence. And that's what we did with the numerical simulation. We just choose initial functions with the parameters. And then we choose the parameters in interesting regions. There we can see the change of long-term dynamics. And then we choose these lambda 1, lambda 2 over an interesting region and do simulation until we can decide on the dynamics, long-term dynamics. So this is what happened. So we choose lambda 1, lambda 2 from these square, lambda 1, lambda 2, and we picked up many values in this range. And we found that if they sit in this range and V vanishes, U survives. In this range, chase and run coexistence happens. In this range, U vanishes and U survives. U vanishes and V survives. In this range of the two parameters, both species vanishes. So this is enlargement of this area. And that's our choice of U0, V0 together with the other parameters. So we actually did lots of simulation. And for each of these points, that's what we did. For each of these points, lambda 1, lambda 2, we run the simulation until we know the long-term dynamics. So that's how we checked the initial function. And that's the trace and the wrong coexistence state. And this red curve represents the density of U, the V species, and the blue curve U species. So this is at time 200. And the distribution for U is like, V is like that. This is close to 1, and here it goes down, it's close to 0. In this range, the strong speed compared to U is close to 1, but then there's a transition, and that's the front of U. So that this is the population range of U. And this is the population range of V. But V, when U appears, so U's population is close to 0. And this front moves with the speed S mu 2 star. And this front moves with C mu 1. And here, that's the range radius. S2 increase nearly linearly. S2 also increase linearly. However, they have a different speed. Therefore, this gap, when t goes to infinity, this difference converts to infinity because they have different slopes. And then more recently, together with Changhong Wu, we looked at this problem again. Actually, this numerical result gives us encouragement, saying that perhaps we don't have many other coexisting states. And then we looked at the situation rigorously. We found actually, indeed, there's another new state, but not anymore. So we have at the end exactly five long-term dynamical behavior in this weak, strong competition case. 1, 2, 3, we know both species are vanishing. 2 and 3, at least one species is vanishing. 4a, that's what we call trace and wrong coexisting. And then we found a new one. For this new one, both species spread successfully, but their fronts are kept within a finite distance all the time. In this A, as I said in the previous page, so this front, the gap of the front, you see, front of V is here, front of U is here. This gap is this gap here, goes to infinity when time goes to infinity. But this new state, these two gaps stays bounded. So that's what's new. How did we found this? So we look at, instead of looking at initial functions, we look at these, S2t minus S1t. So these are the range radius of V minus the range radius of U. But this is just a function of t, and we know there are only 3 possibilities when t goes to infinity. Either this limit to sup is infinity, limit to inf is minus infinity, or the difference stays bounded. And we can show theoretically that in this case, that's what is necessary. Yeah. In this case, S1 implies trace and wrong coexistence, and S2 implies case 3. V vanishes and U spreads successfully. Furthermore, we can show S3 can definitely occur. And therefore, we know we have just, in this case, if A is greater than B, greater than 1, greater than B, we only have 3 possibilities. Either coexistent, trace and wrong, or V vanishes, U spreads successfully, and then the last case is both spread successfully, but their front are kept within a finite distance all the time. And when I say we have 5 possibilities for the original model, I mean including other cases. for example, this is greater than that. Yeah. Now this is a more precise description of this trace and wrong coexistence. We know the two speed, u spread with this speed, v spread with this faster speed, and that's the population density. And the vanishing of v, we have a more accurate description of S1t. It goes to infinity with the speed s mu1 star, but this is a more accurate description. And that's the population density. V vanishes, convert to 0, and u, the population density, is determined by this terminal wave profile. And how do we know each of these cases happen? That is by suitably parameterize the initial function. So if we to fix these pair u0, v0, and s10, f20 are the initial range radius for u0 and u1. If we parameterize v0 in this way to generate a v hat sigma, then we look for solutions of 3 obtained with these special initial data. So v sigma is at 0 is just u0, and s1 sigma at 0 is s10, chosen from here. But with v, it's parameterized. At 0, it v hat sigma, and s2 sigma 0 is sigma times s2. Now we have a family of solutions, and then we can show, with this family of solutions, we can show with the other parameters suitably fixed, and we can show the existence of two constant, sigma lower star and sigma upper star, so that when the parameter sigma is greater than sigma upper star, S1 happens. So we have a trace and a wrong coexistence. When sigma is less than sigma lower star, we have S2 happens. Therefore, V vanishes, U spread successfully. But when sigma is between these two constants, S3 happens. So we know each of these cases, S1, S2, S3 can happen. And we suspect that these two sigma stars actually are the same. So therefore, S3 actually is an exceptional case. That explains why numerically we didn't detect this situation, because this is an exceptional case. Numerically, how could you choose a parameter to be equal to some exceptional value? So that's why we didn't get this new case S3 numerically here. And we expect that, so these are the same. These are the same, and when sigma takes this value, and we have these more accurate result. But this is for what we need to do in the next step. I think I'll stop here. Thank you.
Thank you very much, Professor Yuan. So now we open the turn for some questions or comments. So if anyone has some question, please just do it. So, Professor, I have a curiosity. Okay, you treat the radial case, no, with symmetry.
Yes.
No? What about the case where the no radial or?
Yes. For that, we.
For instance, star-shaped.
Yeah. Now, actually, we didn't do any theoretical investigation for the competition case, but for the one-space dimension case, yeah, for this case, if omega t is not a radial, we don't have a radial symmetry. Actually, in this work, we proved that. So we have a very good regularity for the free boundary, and also we proved that the free boundary for large time, it becomes more and more like a sphere to convert to the radially symmetric situation. For competition model, we did some numerical simulation, and it indicate that it's also the case. Even you start with omega 0, which is not far from a radial. Actually, numerically, we checked the case. We start from something like a triangle or rectangle. Eventually, it evolves, the population range evolves into a ball. In 2 dimensions, it evolves into a disk. So the free boundary becomes like a sphere when t is large. In one space dimension, here, not one space, for one species model, and we have a proof. Theoretically, we proved that's the case. But for competition system, we only have some numerical evidence, not rigorous proofs.
And biologically, what does it mean that the situation?
Yes, biologically, I think because we assume the environment is homogeneous, everywhere things are the same. And then when you spread, eventually you run into, your population range becomes a disk.
Okay.
But in reality, we have mountains, we have rivers, things are different. So then it shouldn't be that case. But in the ideal world, if everything is the same everywhere, homogeneous environment, then your weight and your population range are disks, yeah, spherical. Yeah.
Okay, thank you. Okay, is there any other question or comment?
Professor?
Yes, please.
In the time existence, there are theoretical results for the short time existence. If the boundary conditions on the boundary for
Yes.
short time.
Oh, yes. Well, for the radially symmetrical case, of course, we not only have a short-term existence, we have a long-term existence. But without a radial symmetry, and we can only consider weak solutions because singularities can happen. But for weak solutions, we can prove the solution exists for all time, not only short time, but it's a weak solution. And because singularities can happen, so the solution can only understood in a weak sense.
Which paper, which reference is?
So these two for one species model, and these two consider, this gives the definition of weak solutions. And in this paper, we have a definition of weak solutions, 2 definitions of weak solutions, 2 different weak formulation. And we actually have to use these 2 different formulations to prove regularity of the free boundary. So we proved that, so if we initially have omega 0, then the free boundary, whenever it it runs outside of the convex hull of omega 0, then it's smooth. So that's proved here. Yeah.
Okay, Professor, thanks. Thank you very much.
Thanks for your question. Thank you.
Okay, is there another question or comment? If not, so thank you very much, Professor, for this very nice talk. So now I give the word to Juan.
Thank you, Diego. Thank you a lot, Professor Yihong Du, for your amazing talk.
Thank you.